people. So yeah, today, so I almost got to the completion of this dictionary, of the comparison of the perspective neutral approach in our reference frames with the special activity. So let me this morning maybe complete this this part that I was missing, but let me also maybe complete something on this side here in the gauge fixed formulation that I didn't, I mean, I mentioned it in words yesterday, but I didn't really write it down. So yeah, one thing to recall is, so if you do it in this gauge fixed formulation, the frame changes in special relativity, just reproduce basically standard Lorentz transformations that are where you transform by an amount that's given by the relation between the two reference frames. And then on the quantum reference frame side, you have this picture where you have the perspective neutral Hilbert space, and then you have these reduction maps, which you can do as quantum coordinate maps. They're unitary, so I can concatenate them really like coordinate maps that has the same positional structure, like coordinate changes on the manifold. And then you can unitarily change between any two quantum reference frame perspectives. And that also explains why this whole thing is called a perspective neutral approach, while the Hilbert space here is called perspective neutral because it's really the linking structure between all possible choices of quantum reference frame. So in fact, you can also generalize this construction a little bit more than what I've explained. So here, these reduction maps are unitaries on the full perspective neutral Hilbert space, but you can also have the case, for instance, that a quantum reference frame is not actually defined, or the orientation states are not defined on the full perspective neutral Hilbert space. This is, for instance, the case when the orientation states don't give a resolution of the identity on the full Hilbert space of the reference frame, but only in subspace. In that case, you can really do what you also do with coordinate changes on a manifold, that on subspaces of the perspective neutral Hilbert space, where they both have a domain, these reduction maps, on which they act unitarily on a joint domain, you can still do a unitary on the reference frame change. But it's really, it's very, I mean, it's completely analogous to coordinate changes. And now, what I wanted to briefly mimic is, so here this was for states, but really this here is for observables. Let me just briefly write down the analog of, okay, so there was this quantum reference frame map from yesterday, which you have in your notes. So what I'm going to write down is, for the moment, you just have to swallow that, and then hopefully later today we will understand this a bit better. But you know, the analog of this SA here. So this would be using this twiddled O again, some relational observable that acts on the Hilbert space. And okay, for the moment here, for simplicity, let me just take E, the orientation of the quantum reference frame in the identity. And then you can show, or let me say, actually specialize this for the moment for ideal quantum reference frame. What happens for non-ideal, I will explain later. This will actually be mapped. Sorry, I guess I should do conjugation now. So I have R1 R1 dagger. Okay. Then you can show that you just get Fs in this case. So the gauge fixed formulation of this relational observable. So here it's important it's this old twiddle there. And this here is true for ideal quantum reference frames. Okay? Then you get exactly well, the observable that you insert in here. For non-ideal frames, you get a slightly projected version of this. And you can show that this object here actually becomes, on the other side, again, supposing this is an ideal frame, then you actually get O, but without the twiddle, of Fs are MN. Okay, so it's something that's maybe we'll see later. But really, so this is the really completely. So okay, then the transformation here is V1 to dagger, so V1 to sigma reference frame transformation that I wrote down yesterday. And really, this is the complete analog of this here. So if I gauge fix the relational observables, so the gauge and control, I gauge fix it into the frame perspective with which I have dressed. I just get the bare undressed observable. So that's exactly what happens here. And when you gauge fix into another reference frame that's actually not involved in the dressing, here this is just the sort of coordinate expression of the relational observable relative to the first frame, which is this here. Okay. So here in this case, it is still important that this is this pi pn projected version. This one is the G12 version of it. So why this happens is okay, I have to do a little bit more work to explain why that is so. But I just wanted to insert that here, and hopefully maybe in this hour or the next one, I will explain why this happens. But I just wanted to complete it here that you see it's really also the observable part of this special relativity is also fully fluid. All right, and now let's do the analog of option A, so the gauge invariant way of translating observables or transforming observables. So tomorrow's today. So really what we want to do is basically we want to find a transformation so we want to find a transformation of Fs R1, and let me, for simplicity again, keep it here at the identity configuration of the reference frame. So what we're looking for is something that I will call, well, it's not the same V as here, a Maskell V if you want. So this, which maps this to Fs R2 E for all Fs in this algebra AS. So this is what is happening here, right? So I'm okay in this special relativity scenario. Okay, there's not that many system observables that I have, but really here it's mapping all system observables, all relational observables describing the system relative, in this case, relative to the second frame, to the corresponding observable, describing the same system property, kinematically defined relative to the first reference frame. Okay. So we're going to be looking, so here, the Fs is the same, but R1 and R2 are very different. So it's really, it's a change of relation observable. Whereas this here is not a change of relation observable, it's one and the same gauge invariant observable that I'm gauge fixing in different points. And to this end, I have to explain maybe something first, which is, okay, I realize that I also called this V, but you may remember that I've introduced these reference frame reorientations, which I called V, and they only act on the frame. Now, what you can check, maybe I'm going to explain that now, is so let's first have a look at what happens when we conjugate such an observable by these frame reorientations. And because here, basically what happens, I'm taking one relation observable, and you can view this as a reorientation of the first reference frame by an amount that's given by the relation between the two reference frames. So what I want to check first is how does a reorientation act on these relational observables, and then I will afterwards explain how you do it in such a way that it's given by an amount determined by the relation between the two reference frames. So this here, we had defined this as ER1 this pi pn, and then here in this case would just be this fs, and then we have ER1 g dagger. So that's rewriting that. And now recall that these reorientations, they commute with all gauge transformations, so they commute actually with a pi pn, so I can pull this inside. And they only act on the frame orientation, right? So they don't do anything to the system. And so I can write this as pi pn. And if you recall how I had defined it by this action from the right, it'll translate it to G inverse here. And so that's what I will get afterwards. So this is nothing else than Fs are G inverse now. So you see that what these reorientations actually do, they change the label, the frame orientation label inside the relational observable. So here I had E, and I go to G inverse, and everything else is the same. So really, you can think of these relational observables as, you should think of them really as families of gauge invariant observables, right? It's a whole parameter family of gauge invariant observables, and the parameters are these group labels, these orientation labels inside the relational observable. And so really, you can think of this as at the end of the day, so we have this the algebra of gauge invariant operators on the perspective roof Hilbert space, or maybe I should actually call this IPN, APN. You can really think of these as orbits, these relational observable families. So they're actually multi-dimensional orbits, but the group is multi-dimensional. But yeah, so this is say Fs are E, and then somewhere here all S are G inverse. So the reorientations, they take you along that orbit. And now, when you think about the second kind of observable, describing the same kinematical quantity relative to the second frame, this will be, some other orbits in the algebra. So, so this here may then be O Fs R2 of E. Really, what we want to do is we want to go from here to there. And yeah, we maybe annihilate this stuff over here because I'll need a bit more space.
Excuse me.
Yes.
So in the calculation, you just have that one, and index 1 R1 is not necessary.
Oh, sorry. Yes, this is you mean here?
Yeah.
Yeah, no, sorry. R1. Yes. Okay, so also here, I mean, you have an identity on R2 which I neglected. Sorry, this may happen a few times. So sometimes identity factors will be omitted. I'll try to keep track of them as possible, that I don't forget. So, yeah. So So this is first of all an understanding of what reorientations do to these relational observables. And what we want to do is basically mimic this feature here, that we transform, so we reorient a given relational observable by an amount that is given by the relational observable describing the relation between the two frames. So let me first of all, so we want to reorient by amounts given by relation between R1 and R2. And and what we will be interested in is, for instance, the relational observable where I'm going to describe the second reference frame relative to the first. So for instance, I will be interested in our case, yeah, let me maybe write it like this. R2 relative to R1 of E. Okay, so I'm inserting now the second reference frame here into the relational observable, the conditioning on the orientation, and I want to describe that relative to the first reference frame. And what does that give me? Well, it's just pi pn, and well, it's pi. Pi. Okay. R2 identity on S. So now, so this will be the amount, or basically what we want to do now is we want to do a transformation from one frame to another, or reorient. We want to do a reorientation conditional on the orientation between the two reference frames. And so let me maybe write this down. So R1 to R2. So here there's this block for inserting some arbitrary observable, relational observable, I should say. And now that's called G prime, sorry. So, and I'm going to insert this guy here, phi of G, phi of G, 2, 1, E. And then I do a frame here, sorry. Yeah, sorry. When I insert it now, I want to put in a G prime. So that means I'll just put a G prime in here. And then I'm going to do an R1 G prime. Then I put my observable in here. And then I have the R1 vector. So I think that's correct. Let me double check that in my notes, but I think that's correct. So basically, I'm going to do, sorry, I'm taking a G prime. So this is actually now a G twirl over frame reorientations. So an incoherent group average over reorientations, that's this here. And it depends on this relational observable here that describes the relation between the two frames. So I'm describing the orientation of the second frame relative to the first. And conditional on this, there's the G prime in here. I'm reorienting the first frame. Okay? So this is really, you can think of this really as the analog of this object here. Right? So you're reorienting one frame by an amount that's given by the relational observable describing one relative to the other. And so, yeah, so you can spell this out. This will be prime. So here I'll have another QGG double prime that comes from this pi pn, and then this up here. So this guy, G. So I think actually this G now I want to set to, when I want to go to the identity here, I have to set this G to the identity. But let me keep it like this for a moment. And then the other one, correct. So let me just double check that I didn't make a mistake here. I think that should be the correct result. Actually, sorry, I think I missed something here. Again, so here, G double prime, of course, I should have, yeah, sorry. So here I'm of course missing the G double prime. And that comes from inserting this back in here. Sorry about that. Right. Yes. Double prime G prime. And here I should also have I also put that here. Sorry about that. So G double prime G double prime G.
When you insert IPN, is it very unitary?
Excuse me.
If you
Oh yeah,
insert
yeah. Okay. Sorry. Actually, you're right about that. So you're right. When I insert IPN, I would have only on the left side, not on the right side. So in the note, I mean in the paper, we did it a priori in the kinematical space. So we did it with G twirl. So actually, would have been the untwiddled O.
Okay.
But that shouldn't actually matter in this case. Yeah, you're right. Maybe I should. It should still work without this here. Yeah. Yes. And the rest should be okay. I think. Yes. Yeah. Let me just make sure that I'm not here. So you see why I did want to do this yesterday in 2 minutes, because you have to be a little bit careful by this. But that should be the correct thing. So if you apply this to the to physical states, or you evaluate it on physical states, that should work. So so again, in the paper we wrote it in terms of the full G twirls for both observables and reorientation, and then you can prove that this happens. And I should say actually one more thing that I forgot to say is, so far this transformation we've only worked it out for ideal point reference frames, so that's actually important too. So that these are orthonormal. Okay, so if if the corner reference frame is not ideal, it's a priori not clear how this works. There's a few subtleties in there. I mean, it's not the statement. There's no way that you can write this down. It's just basically for ideal corner reference frames, the reduced algebras S relative to one prime and another, they're isomorphic. So you have a nice relation between the two, and that's given by this thing. But in general, when you have non-ideal frames, then the algebras actually need not be isomorphic. So you will not even have a nice well, you won't have an algebra isomorphism between the two, so you will rather have some kind of channel. Okay? So that certainly exists, we just haven't worked out. But anyway, so the thing is that one can now check that if you let me maybe put here a G label for this orientation of the second frame that I've inserted here. So if I put this G to E, that I get when I put OFS R1 relative to E inside, then you can check that you get what you want. Or maybe, I mean, okay, you can leave it at G, it does not matter. So to show this, I mean, it's not super difficult, but I think that as an exercise. Also, will require a couple of lines to write down. So, and
Excuse me.
Yeah.
So in the second line and from the bottom,
yeah.
that one, and all the indexes are R1.
Oh,
It's
no.
okay.
Yeah, sorry, no, this is okay. This is R2.
Okay.
Yeah, sorry about that.
I'm sorry, and I'm still don't understand the why and this one corresponds to the box equation.
Okay, so
Yeah.
so here, what are we doing? We're taking relational observable, describing the system relative to, okay, in this case, the second frame, that's the first. So here we're doing it the other way around, but you have a relational observable describing the fixed kinematic observable S relative to one frame. And then you get the relational observable describing the same kinematic observable relative to the second frame via a transformation, which you really can view as a it acts on the frame index. You can view it as a reorientation of this frame here by an amount, by Lorentz transformation, the amount of which is given by the relation between the two reference frames.
Mm-hmm.
So you can view it as a reference frame conditional frame reorientation. So this is what this here is in the quantum theory. Right? So we have this here is a reorientation of the reference frame. It changes these relational observable labels. And now we're not just doing any old reorientation of the first reference frame, but we were doing it conditional on the relative orientation of the two reference frames, and that conditional is given by this observable here. This is a relational observable that describes the different frame orientations of the second frame relative to the first one in the Gaussian band way. Okay. So that's given by this thing here. And now, so basically we're combining that relational observable that describes the relation between the frame orientations with the reorientations here. But we're integrating all the G primes here, and the G prime sits inside here. So okay, if you were to evaluate that on a state again, then the state has some information about what the relation between the two reference frames is in that state. So you should always imagine, of course, that it acts on some neutral state. And that's, this observable, of course, encodes as an operator the relations, but whatever the relation is depends, of course, on the state that I insert. Right? And this is really a conditioning operation here. So, and because here in this case, as I said, we're dealing with ideal quantum reference frames.
Where do you use such condition from in that equation?
Which equation? This here?
Yeah.
Here.
Yeah.
So this here, because when we have ideal quantum reference frames, then these are really orthogonal projectors.
Orthogonal,
I mean,
I see.
projectors in the sense that, okay, in general, they're going to be delta function projectors. But so they're going to, when you write the perspective group of the physical states on which this will act, you know, because it's orthonormal, it will just pick out all the, you know, only those, the states will pick out within the transformation only those frame states here on which it has support. Right? So that I'm summing over the frame orientation states here. And so when I act on the physical states, you know, the average over the whole group may actually become only an average over some of the elements in the group, because the state doesn't have support on all of these elements. And that depends on this relation observable that describes one frame relative to another. So in that sense, really you can think of this transformation as being something that reorients the first frame by an amount, or conditional on the relation between the two quadratic frames. Right. So yeah, I realize it's a bit subtle to explain this, but it's really you can check that this works. You know? So,
Thank you.
So the details, you know, that this is true, you can check in this paper. I'm just going to reference it now. So, like I said, in there we discussed this actually for even. So for ideal quantum reference frames, turns out there's not really a big difference between the G-twirled and the projected observables. So of course one only has support on the blue river space, the other one also has outsides. But the algebraic properties of these observables are basically the same otherwise. And so there we work this out without even thinking of what kind of states they act on. But in the way in which I wrote it, you know, when you act on physical states, this is equivalent to the G-twirl. So if you evaluate this thing here really on physical states, then it's just using my quality for all physical states, all respective physical states. So again, if you want to see the details of why from this expression here, this follows, you can check that reference. It'll be a few lines for you to check that. But anyway, so this is the ideal quantum reference frames, the common version of this here. So you're really changing, so you're really satisfying this here for any system. So that's exactly what this here also does. Okay. So much about the about this transformation A. We're not going to be using that further on. I just wanted to complete this analogy. Let me maybe, as a next thing, give you one illustration of these quantum reference frame transformations. The first kind that I wrote down in a very simple case, so you can see what it actually does. Are there any further questions on this before I do that?
Just in case, in the last equation, I'm sorry, you already erased picture, and you wrote and the full two orbit line.
No, here. Yeah.
That one. Yeah. So in the
that's correct. Yeah.
Yeah. So in that one connects to where and where?
From here to there.
There. Okay. E and E.
Yeah, well, okay, here in this case, the way I wrote it down, I went from E to G.
E to G, okay, yes.
So, but the thing is, you know, you can always write it as going from E to E and then doing a reorientation on the second frame.
So the two effects are already included there, right?
Yes.
I see. Thank you.
Okay. Yeah, so then any further question on this? Otherwise, I'll just go over to an illustration of the first kind of non-reference verifications. Yeah, let me, so if there's no question, then let me eradicate this. So, sorry, I'm going to stop there for a moment. So, so let's go back to this example one, or somewhat extended if you want. So, so let's suppose we have H, well, let's call it R1, R2, and HS. All these HA are some L2 over R. So yeah, you have the reference frame, so A, S. And let's have G, the translation group again. Yeah, and we have now the total constraints given by Q1 plus Q2 plus PS. That's the translation generator, so we have one or two, and then some system S, three particles on the line. And let's have a look at these transformations here. That's okay. One thing that I should say is, so I'll explain that a bit later, but you can already see the intuition of it, that this respective neutral Hilbert space is going to be isomorphic to two copies of these kinematical subsystems. So, yeah, or Y. Let me maybe write it down. So here we will have the translation group is R, with Dx, and then U of X. And this is Px to the I X P total in this case. And so can formally write this as the delta function of the total momentum. And now, so here the kinematic Hilbert space is therefore, it's an L2, or it's isomorphic to an L2 over R to the 3. And I can take, so formally I can, write down some physical state as IPN times some kinematical state. And I can simply take the momentum representation of the state. We could have EP1, EP2, EPS. So I'm citing P1, P2, EPS. Then pi Pn is just the delta, so P1 plus P2 plus PS, acting on P1, P2, PS. So in the momentum representation. And now you can see, okay, I have this delta function here, and I can inside an integral, and I can solve this delta function many different ways, right? So I can solve it for P1, I can solve for P2, or whatever you want. And so, so for example, So then we get, so this is, for instance, we want to take particle 1 as the reference frame. And the natural thing to do is to solve this for P1. So we have P2, PS, and then in here, P1 is then minus P2, minus PS, P2, PS. Here, minus P2 minus PS, P2 PS. Now the question is, of course, how do I normalize that thing? And okay, that was actually what I wanted to describe later. So, I mean, this is a clear example of the states. You know, this round bracket psi that is not normalizable in the inner product of the kinematic Hilbert space. Right? Because I have now the momentum eigenstate of this total momentum. So the improper eigenstate, it's not actually a distribution. Right? So, so this is not normalizable in H kin. The P total momentum eigenstate. I actually can't explain this for this example at this moment, but I suppose since I already started, I do this. So, so that's an example, or when you write this, so I'm writing this in a somewhat sloppy physics way, and maybe later I'll explain more precisely how to solve this. But really, you can, so we need a new normalization for these states. Okay? So once we have solutions, where we have these gauge invariant states, these round bracket psi's, so they're not elements of the original Hilbert space, but I want to build a new perspective neutral Hilbert space, so I have to give you a prescription of how I can actually normalize them. And so we need a new inner product to define HPN, which is now not the subspace of HPN. So really it's improper eigenstates, so they're distributional. So the way you can do this is describe it like this. So you will basically the matrix element of this Pn, so round brackets is the physical inner product, and angle brackets is the original inner product of the kinematic Hilbert space. Okay? So so physical inner product here is the kinetical inner product. I'll explain a little bit after this why this is a good to do. Now, sorry, these psi kin and phi kin are any kinematical states that under the map pi Pn map to the physical states psi and phi. So here, you know, I have a psi kin that maps out of pi Pn to some state, some physical or perspective neutral state psi round bracket. But in general, there will be many different states that map to the same. Okay, it's a many-to-one relation, so there's really going to be an equivalence class of kinematical states that correspond to the same physical state. And the point is here, you can insert whichever member of the equivalence class that you want. And maybe to see this is that, I mean, you know, a priori, so you can basically see this from here already. So, you know, kinematical states, so these are going to be square integrable wave functions over 3 variables. The a priori has three independent, it depends on three independent variables. But then down here, these physical states, they no longer have a dependence on three independent variables, but this here is actually fixed. Right? So the first variable is fixed once you know the other two. Okay. So, and there's of course many kinematical states that may differ at this level, but then whenever this variable is fixed to be given by this minus the sum of the last two, gives you the same value. There will be many states that have that. And each and any one of those states will therefore give you the same physical state. Yeah? So it's a so this is a many to one. I mean, so when you have a compact group and this pi pn is a literal projector on the kinematic group space to subspace, is also clear, right? So you go to subspace, it's a many to one relation. And so this here is no different. Yeah, so is that clear, the argument? So it's really, here you have an independent, or the dependence on three independent variables, as the square integral. Here you really have only a dependence on two independent variables, and this slot is fixed. And there's many such wave functions that even though when you let pi1 run independently from the others, okay, they may differ, but for always when I evaluate it on the configurations where p1 is given by minus the sum of these guys here, there are many states that will have a certain answer that differ when p1 takes a different value. So that's why this is many to one. And the point here is, again, you pick any member of the equivalence class that maps to this psi, and you pick any member of the equivalence class that maps to that pi. And then the other thing is that, formally speaking, this object here is integrating all of R here. Formally speaking, it's symmetric with respect to the kinematical inner product. That's why this works. Okay, so so this guy here is really given by this delta p total, and then when you insert these features here, let's call, maybe before we go there, let's call this here this what I'm inserting in green. Let's call this psi tilde. Let's just call it psi tilde. Well, psi tilde of, sorry, p2 yes. What you will get here is that this is a dp2 dps, and then you will have a psi tilde star p2 ps and a phi tilde yes, so it's what you will find. So again, this phi tilde is defined then in the same way as I'm defining this here, or this is again, so here you see, again, this is basically encapsulating the many to one relation, and these guys are square integrable. So these guys should be generically square integrable. So there's some subtleties about null states that I will discuss a bit later, but square integrable. So that means, here if you look at this state, psi, when I write it in this kinematic way, I have two integrals, but I have three slots here. So when I don't put this delta here, and I was just to in a kinematic way, smack these two physical states together, I mean, I will always get a delta of 0. I would always get an infinity. But if you define it in this way, so really you can also formally write this here as psi kin, and then it's a bit, loosely speaking, you can think of it this way. You can take this here as the physical state phi. So you can see I'm taking now not within the kinematical sense of the inner product, that's mapping two physical states on one another, but I'm taking a physical state and I throw a kinematic one. But really, a more precise mathematical way you will see is that I should actually think of it the other way around. That I have the phi kin, sorry, because these physical states are going to be distributions, I can integrate them up against physical states, against kinematical states. So in fact, you should really do it the other way around. I'll explain that in the next while. But for the moment, this is this kind of formula that I have to operate. So anyway, so this gives you kind of an intuition of why we're going to get it L2 over R2 when the kinematic grid space was a L2 over R3. So we're basically getting rid of one independent variable by solving for the constraint. And it's intuitively clear. Classically, the same happens, right? I can solve this constraints for P1, so I have then only P2 and P3 as independent variables. And since it's a gauge generator, I could use Q1 as a gauge fixing variable. So I solve the constraint for P1 and I gauge fix Q1. So I've gotten rid of the one pair. And then I'm left over with P2, PS, and Q2 and QS as free variables. So I have a four-dimensional phase space that's left. And when I quantize that, I would want to okay, so that's the intuition why we get these an L2 over an R2 that we get as a physical Hilbert space.
Excuse me.
Yeah.
Is the norm of psi 1 if original kinematical state is the norm as well?
Well, yeah, not necessarily. Yeah. So you wouldn't have to normalize again in this inner product. So the kinematical norm, from the point of view of gauge theory, doesn't really matter. It's at the end of the day, what matters is the normalization in the inner product. Although actually, maybe the way I've written it, maybe it would actually be normalized. So I mean, so typically also when the projector is a proper, sorry, when this pi PN is a proper projector, when the group is compact, unlike here, then when you define it this way, then of course the projector will not, afterwards it will not be normalized in general. Right? Because there will be some states that have support outside that were normalized before, and then part of it is projected out, so afterwards it's not normalized, so that means you have to renormalize the states. So the same will also happen here. All right. So now I wanted to come to this to these quantum reference frames. I guess I can. Yeah, let's take this in just one. So this is one. 0 in this case, the identity of the translation group is 0. So we would be setting Q1 to be equal to 0. And then we have identity on the rest. And here R2 would be given by 2, 0. And you can check, actually maybe let's just work this out now. So if I, if you look at this state here, this physical state, that's R1 of 0, some state psi. So I have this Q1 0 there. is gonna hit this guy here. And yes, yes, and then yes, and then we have this y equals 0, and I'm factoring it out. Okay, so this is going to yes, minus p2 minus yes. So I'm just isolating that factor. And this is 1 over square root 2 pi. We have general inverse where QP is well, square root 2 pi to the, okay, don't quote me on the sign here. In our case, fortunately, it doesn't matter because Q0. So this follows from the commutation relations, canonic commutation relations, they get something like plus QP. In our case, Q is 0, so that's why it's just a modulus 2. And that's, by the way, here in our case, the renormalization of the that you were asking for. Then we just compare, so that we just basically compare. So this here is psi 2s at 0. So you could do the same thing here. So yeah, you would get a similarly simple expression where you would have solved the delta function for P2 rather than P1. And so here you would get somehow some states. Yeah, actually, I'm now with a. And now the quantum reference frame transformation that goes from here to there. So U1 to 2. So I'm just quoting what we had yesterday on the board. So I've written it down for general groups. But here really I'm reinserting. This is just in a special case the quantum reference frame transformation of it yesterday. Now, let's have a look at a specific state. So, what this actually does. So, let's take some unnormalized states. So, we could, for instance, take a state that let's go to one perspective. And so let's suppose we have that the second state, that the second reference frame is in some superposition of positions. And then the system particle could be in some other states. But it's also positioning state. And then we can act with this E1-2 map on this. Before I go into this, let me just double check how many signs there is. somehow in my notes I have a minus sign here. I think that yeah, so I have a minus sign there. I mean, this here now is US of G, and okay, I probably someone will mention that here the other way around. Okay, here it doesn't really matter because I'm integrating with the whole thing. Yeah, no, it is important for getting this right here to be consistent with that, because I have e to the minus I px acting on 0 gives me plus x, not minus x. So there actually needs to be like this. Okay, so anyway, so acting on this here now, what will happen? So we're going to have this dx, going to integrate over r. And then we're reinstating the one factor, and then this guy will act on this here. Okay, so this is now, of course, no longer a tensor factor. I'm annihilating the 2 factor, and so here minus x in addition with this here will just be okay. It's x plus y plus z. Delta function of this here, and then here I have delta function of x plus y. Yeah, and then I have this w here, but it's going to be translated by x, so I have w plus x. So now we can just solve this integral here over x, the delta function. So we have to do the first piece. We're going to have minus y minus z. The first reference frame, and here tensor w minus y minus z, and then we have so this is the system plus. So in this guy, so it's just the same without z. And y. Okay. So you see this, this is the product state. Product distribution really, and this here is an entangled state. What you see is that these reference frame transformations, they will in general change the entanglement structure. So they can map product states to entanglement states and vice versa. So here, what is in particular important is, so you have a superposition in the second frame relative to the first frame, and that superposition is translated into the entanglement of the first frame with the system relative to the second frame. So you get a relativity of entanglements and superpositions. So this was kind of one of the first examples of reference frame transformations in the paper. And so on. They didn't use this perspective neutral framework, but they proposed them in other ways. We later reproduced it using the perspective neutral approach. And okay, that's in the foundations community created a lot of excitement that you get frame relative different kind of positions. Okay, so now hopefully in the second lecture today I also explained what really the proper reason is of this, and it really has to do with the fact that these reduction maps here on reference frame perspective are nothing else than the tensor product structure on the gauge invariant Hilbert space. And the chain of quantum reference frame is nothing else than a change of tensor product structure. So it's a change of subsystem partition. And that's the reason why I get relativity of correlations and so on. Any questions on this?
But I have a question.
Yeah.
So you more or less create entanglement state from product state by kind of changing reference frame.
Yeah, well you can do
So
it, yeah.
can you always create entanglement from product state, or is there any some product state that cannot create the entanglement state? But why are you changing reference frame?
Yeah. So for instance, if I neglect this part, I have a product state and I'll have a product state afterwards. So it's important that here in the first state I have a superposition of the quantum reference frame relative to of the second reference frame relative to the first. If I don't have that, it has to be. When I say it has to be the superposition, it has to be the superposition in the frame orientation states relative to the first.
Okay,
So superpositions and frame orientation states, they will always translate into entanglement.
So the superposition on the second side is necessarily sufficient to create entanglement.
Sorry again.
The superposition in the second side, sorry, the first part, yes,
Yeah.
is necessarily sufficient to create
It is sufficient. Is it necessary? I think it is also necessary. Yeah. So we actually looked at these questions in finite dimensional systems with finite groups, for instance, where you can do stuff much more rigorously. And we wrote this a couple of years ago. I forgot the precise details, but I think it's probably correct that it's also necessary. Yeah. So if you have an initial product state, there's no superposition in the orientation states, then you don't get an entanglement state afterwards. So it is necessary. But again, we have to talk about superpositions in the orientation basis.
Second, if it's possible to generate this frame, I mean that what you have is a mixed state, or it's only works for pure state?
The quantum reference frame transformations, or
Yes.
Yeah, you can do it for mixed states also.
And if it's sufficient for even for mixed state, the creation of entanglement is sufficient.
Okay, yeah, that's a more complicated question. Yeah, I mean, entanglements here, of course, for mixed states are a little bit more subtle. Yeah, off the top of my head, I don't think I know the answer to your question, because you can have, of course, mixtures of all kinds of states. But I think, yeah, I mean, okay. I mean, what you're asking is basically if I have a mixture of product states, and I guarantee if there's no superposition in the orientation state in any one of them, that I get again a mixture of product states in the separable states and separable states.
In a necessary sufficient way.
Yeah,
and
so I
this
think
is
actually,
kind of
I think
LOCC
actually
operation.
probably it's still true, because you
It's
can.
kind of LOCC operation, right?
Sorry?
It's not LOCC, but it's kind of, it never creates entanglement from any product
Yeah,
state.
yeah.
It's
No, I
kind of
think-
reminds me of LOCC.
No, I think it is still true, because you can, this operation is unitary. It's linear, so you can do it for each part in the mixture independently.
Yeah, it's very non-trivial, but this transformation is LOCC.
Is what?
This transformation is LOCC. It's very non-trivial.
That it's unitary, you said, or?
I mean, because you apply unitary, right?
Yeah. So this is unitary. That's right. Yes. Yeah. So actually, the statement is, of course, that if it is true for pure states, it will also be true for separable states in general, because you can do it for each part of the mixture independently. So you have a mixture of product states. You guarantee that you get a mixture of product states, provided that each of the product states, of course, satisfies the condition that in those product states, the new reference frame doesn't have any superposition in its orientation states relative to the first. As long as that's true, you want to generate any entanglement. So you always map separables to separable states.
Excuse me.
Yes.
Can you define entanglement between reference one and system without gauge fixing?
Yeah, you could do that. So I mean, well, yes. So I mean, you could do this also in algebraic ways. Okay, so actually maybe I'll get to that later. But the thing is that really this was meant to be just an illustration here. So you can do this more generally. So that was related to subsystem relativity. And tensor product structures technically you can define in terms of unitary maps, but you can also define them in terms of observable algebras. The observable algebras you could formulate directly at the level of the gauge invariant theory without ever talking about the gauge fixing. So then, but it turns out that if you define it that way, it's equivalent to defining it. So, and the other thing that I should say is, the tensor product structure is not just given by a single unitary, it's an equivalence class of unitaries. And so, even though, I've used a particular gauge fixing, so okay, what I forgot to say, I guess, really important, is, so here, this will give you actually, in this case, H1 tensor H2, HS, sorry. And here, this here will be H2 tensor HS, when I have here on the top HPN. So what I do is conditioning. I mean, it's maybe clear from this picture here already, but I will actually get the full tensor product of the kinematical Hilbert spaces of 2 and S, and here of 1 and S, and there's no further restriction on it. So this is actually, so it's going to be a unitary map from some abstract Hilbert space to a tensor product. And here again, it's a unitary map from some abstract Hilbert space to another tensor product. So that defines the tensor product structure in an abstract way, but you have to guarantee that if I now change the gauge here, that the tensor product structure doesn't change. And it's true that it does not change because if I change the gauge here, that's equivalent to doing a local unitary on this here, but that doesn't change the tensor product structure. So that's why even though I use a gauge fixing to define the tensor product structure, it is a tensor product structure on the gauge invariant Hilbert space. It is a gauge invariant tensor product structure. So you use the gauge fixing, but it doesn't depend on the gauge. So it depends on the choice of quantum reference frame, but the choice of quantum reference frame is not equal to the choice of gauge. So I must be careful with that. All right. Any other question on this? Yeah.
So physically, this means that when you choose one reference frame, the state is productive state, and when you choose another frame, and it becomes entangled.
Yeah.
So according to your different frame, you will the state have different entanglement.
Yeah. Yeah. I mean, okay, here, this is done with distribution, so it's a little bit fishy from a mathematical side too. Because talking about products of distributions is not quite the same as products of Hilbert space elements, but you could do the same thing, of course, in a more sophisticated way if I steer the states and do wave functions. But this is just to kind of illustrate the idea, right? But yes, this generalizes also to proper Hilbert space elements, not just distributions like this here. And then indeed the statement is if I look at the system and I want to ask what's the entanglement entropy of the system, relative to the first frame where your product states are 0. If I go to the second frame and I compute its entanglement entropy, it will be not 0. So the entanglement entropy changes. That's the entanglement entropy calculation.
Is this consistent with the standard results in the entanglement entropy?
Yes. So part of the next lecture is what I'll explain that. So the importance is I have gauge invariance, but I still have frame dependence. So that's very important. Sometimes, also when we think about, for instance, general relativity, we think about frame dependence and I choose different coordinate systems, but okay, maybe that's not quite gauge invariant because I'm talking about coordinate systems that are higher than they have physical meaning. So this is stronger. It's frame dependent but gauge invariance. Both. You can do the same in GR. It's just that at the end of the day, so I hope that I will get to it, but but the main point is that there's no unambiguous way of defining the gauge invariant subsystem structure when you're given a kinematical subsystem structure. There's no unambiguous way. It means in general there's a continuum of ways, and each one of them corresponds to each other's point of reference frame. Okay, I think I have to scale down my vision of what I'm going to do in this course. So my aim was to actually still back up some of the statements that I made in this comparison, give you a little bit more of an understanding why these maps are unitary and so on, how observables reduce. I'll try to do a good part of it. Maybe I will not be able, for time reasons, to prove all of that because I still want to go into applications of this formalism. But I guess you don't really want to see formalism, but maybe also what you can do with us. And so if you want to go there, I may not have time to actually prove all the statements that I made in the comparison. So, but I do want to come back a little bit to this discussion why we go to the stronger notion of gauge invariance. I forgot which one was the U. So this was maybe okay. So everything that we did so far was the first part of the lecture. So some details on the PM framework. And so one question is, so maybe people familiar with gauge theories and gravity, then maybe it's clear, but why invariance in the strong sense that we have u of g psi equals psi, as opposed to for instance, rho u of g equals 0. So let me say, of course, for all g and g. So rho, some quantum state, so it could be, for example, so this here is the PN approach that I've been describing. So it was important that we actually we go to this strongest sense in invariance in the quantum states, and this one here is the method. This is the QI, the extra particle approaches, plus the operational one for compact G. So the QI, well, let me just put it for in modular G, okay, and for the operational approach, they also pick this method of invariance. It's the starting point of their approach. They do more sophisticated techniques of what kind of states I'm going to look at afterwards. But the story for compact G begins with this. And is that clear that this is a weaker condition than this? So I mean you can see that. Suppose this is true, then clearly, if I build a ket bra of this, it will satisfy that, right? But the converse is not true necessarily. So for instance, I could have some states that are not exactly invariant, but maybe they're invariant up to phase. When I take a ket bra, it's going to be exactly invariant. So that's one example. You can see that this is a weaker condition. So this is really, it depends a little bit. So in general, you cannot say that this is better than that or vice versa. It depends a bit on what your premises are. So in our case, we really wanted to wipe out any external reference frame information. And we wanted to mimic special relativity. So special relativity, you could do this gauge fixing. You know, we align the external reference frame with the internal one, and it's invertible. So I mean, any gauge fixing should be invertible. You can do another gauge transformation to map to any other gauge. And so let me now explain why this here doesn't allow you to do gauge fixing. It doesn't. The second method, this weaker method, is not capable of having invertible gauge fixings. Okay, so that's why you cannot use the second method.
Yeah. Why do you push the comment? Do you mean u rho minus rho u dagger equals 0?
No, I really mean this.
Not the u dagger.
Well, I mean, it's the same. No, so you mean u rho, u dagger? But it's not 0. It would just be
Equal rho. But it's not the same as the comment.
Oh, this is equivalent.
Yes.
So it's invariance in the conjugation sense. This is invariance in the exact sense. So it's weaker. Okay, so let me maybe illustrate this a little bit. So, and I think for illustration purposes, let me assume G is compact to illustrate Y. Because then the G twirl is a projector on, so here when we take the second row, I mean, we're really talking about algebras, right? So I mean, these are operators. And this here, you can really, the G twirl is the orthogonal projector. So it's the G twirl. Your orthogonal projector from, I guess akin to akin G, meaning the G invariant subalgebra of akin, which is just the image of this G twirl. So when G is not compact, it's not quite true. Okay? Because there's, I mean, at least this relation is not true because of divergence issues and so on. I want to discuss. So, and this is your orthogonal projector. So in particular, this means, formally speaking, G squared equals G. And we also have G dagger equals G. And when I say orthogonal projector, I mean with respect to the Hilbert-Schmidt norm. So, so that's the Hilbert-Schmidt norm on So, so that this is an orthogonal projector. Okay, this is not very hard to check, but let me not do it in practice. I mean, so the first and second condition are really simple to check. Because I mean, this really has to do with the fact that I'm integrating over the full group, and I conjugate by u dagger. But if I have a unitary representation, then u dagger G is just u of G inverse, and I can do some relabeling of group elements and so on, and you can see that that's true. Now, what we want to do is we want to consider two G equivalent states. So we can pick, for instance, let's say psi 1 and okay, I'm gonna write. Yeah, why not? Let's. Let me also assume consider two G equivalent states plus a ideal of the reference frames. So here I'm just going to put phi of E here. So this is a little bit. So if the group is finite, it will be an actual Hilbert space element. And that's very too much about this here. And then they have some system states. It doesn't have to be any system state. And then we can consider psi 2, which is just some UG times psi 1. Okay? I just pick some G such that G is not the identity. Okay, it should also not be the isotropy group of this guy. Maybe I'm just gonna keep it like this. So I said it verbally. So it should be the isotropy group of the quantum reference frame. So quantum reference frame orientation states, they can have stabilizer subgroups that leave the orientation invariant up to phase. I mentioned that before. In general, we have to be careful that something like this can happen, but here I'm going to assume that that's not the case. So clearly the two states, so they're related by an external reference frame transformation, and so we should be so they're by premise internally indistinguishable, right? So and now we can consider two density operators. And let's consider one to be let's consider one to be given by some A squared. Let's call this 1 plus B squared rho 2. So maybe some non-zero coefficients. And rho 1, rho 2 are just the density operators, so rho I is just psi 1, psi 1. Sorry, I.
Yeah.
Yes.
Yeah, sure, you can continue. Yes.
So here, so basically what I'm doing is I'm taking a mixture of these two gauge equivalent states, but I can also look at a superposition where I'm looking at A psi 1 plus B psi 2, and then A star. So I'm taking a mixture of two internally indistinguishable states, and I'm taking superposition of them. Okay, so that's what I'm doing. But really, truly speaking, they shouldn't be indistinguishable, these two states, without recourse often to an external reference frame. And now you can check that we find is that rho, when I G12 this rho, that is not equal to the G12 of this rho 2. Okay? So really what this comes down to is, what goes into this is, and you see there's of course, the diagonal pieces here they're just equal to rho. Really, this is just rho plus delta rho. And delta rho is basically the off-diagonal bunch here, so it's A psi 1, psi 2, sorry. So this is A of this guy, then B star, plus A star B, psi 2, psi 1. So it's clear, the first part here is just the other one, so obviously that will give the same answer, but the point is that G of this delta rho is not 0. So this is something you can check. So I mean, recall that this G is just QG, U of G, and then U of G. So we can do this as an exercise. So what I'm making use of is here. So there's these frame orientation states here, and in this one here there will be a frame orientation state with a frame orientation translated to G. So this is off diagonal in the frame orientation states. So this one here, this has a phi of E in there, and this one here has a phi of, so here I'm talking about this G, so not to be confused with that one. So this one contains a phi of G. So this sits inside, of course, there's still something else in there. And the point is that this G12 is incoherent twirl, it doesn't annihilate this. Okay? So that means even after you group average in this incoherent way, two states that should be indistinguishable, when you don't have recourse to an external reference frame, they remain distinguishable in different states. And now, if you want to gauge fix, I'm going to put quotation marks here because it's not a true gauge fixing, but it's not going to be invertible. So we can think of let's call it 1E. I'm just going to conjugate by so I'm just going to conjugate operators by the conditioning on the frame orientation being at E. Okay? So in the identity. So this is really for operators. We have a lot of what we did in special relativity. That you have something like this. Right, so I'm setting the tetrad to be in the identity configuration. So here, if I wanted to do this at the level of density operators, I should be doing this here. So it's a ket bra, not just a bra. So, so this would be the analog of this gauge fixing. Another point is that if you look at this gauge fixing of these two states, it gives you the same result. So I have these two states that are both gauge invariant in this weaker sense. They're different. I gauge fix them, I get the same state. So clearly, this gauge fixing operation is not invertible. So this is because I run E acting on this G delta rho. So here, the G of this delta rho of this guy here, this is non-zero. But the thing is that here I'm conditioning on this. This only contains off-diagonal pieces in the reference frame. But now I'm conditioning on the being diagonal, so this guy goes out. And so pi 1e was not invertible, so it's no problem gauge fixing. So meaning I'm actually losing information when I do this gauge fixing. So this is the reason why if you want to mimic what happens in special relativity with internal frames, you cannot do it this way. Okay. So that's why also why all these other approaches that I mentioned here, they can't mimic this covariant structure of special relativity that I illustrated. So it's really something that singles out the perspective neutral approach. Now you can gauge fix these states. Okay, I'm not going to explain that now, so I'll do that after the break. But to those of you familiar with gauge theories, that should be clear because those are the gauge invariant Hilbert spaces of gauge theories, and of course the gauge theories I can always gauge fix. Okay. There's a few extra words I will say after the break about also how we can think about these things in terms of equivalence classes. That's sometimes a little bit useful. But I think for the moment I'm going to leave it at this. But really the conclusion that you can take from this is that if you go this weaker way, you're kind of implicitly still distinguishing states that you shouldn't be able to distinguish if you don't have access to the external reference frames. So that's this thing. So operationally, when I don't have access, really these states here, by assumption, they're internally indistinguishable. They're just related by an external reference frame transformation. So I should be able to operationally distinguish well until the solution. So that's why, in this sense, you can say that these other approaches are not fully external framing. So this is also the reason why I said at the very beginning that the perspective neutral approach is the most radical about external frame independence. You're treating it as gauge, and you end up with small state spaces and observable algebras. And this is one way to see it. Because there's a stronger condition, there's less states that satisfy this than that. So you get smaller state spaces. And the same is true for algebras, you get smaller algebras. Because we ask for a stronger sense of invariance. And I think I'll say a little bit more about this in terms of equivalence classes afterwards. This is one way in which you can sort of formalize this kind of hand-wavy things that I said in the very beginning about the most radical approach. Yeah. So I'll continue after lunch.
Is there any reference addressing this difference in detail?
This year, yeah. So this one is discussed, and so I mean the argument that I gave here, this is in this paper 23 that I gave yesterday. I forgot what the So after the break, I'll give another perspective on this. That's not in that paper. That's yet another one. But, and then, okay, there's a. So again, I just want to emphasize this doesn't invalidate, going this way for other purposes. So they may have good reasons to do that. It's just if you want to mimic stuff like that.
So this basically means that although when you agree to this G, rho and rho 2, they are different, but they are basically in the same gauge orbit.
Well, they are no, right? So I mean, okay, we'll see that after the lunch break. I mean, they are in different equivalence classes, but equivalence classes defined in terms of that notion of invariance.
But if they are not in the same equivalence class, then when you gauge fix them, they should be different.
What, sorry?
If they are in different gauge equivalence class, when you gauge fix them, they shouldn't be equal.
Yeah, well, that's true when you're on the gauge invariant Hilbert space.
Yes.
What you're saying is true then, so that's true in the perspective neutral approach, but here not. So really, the thing is that, yeah, I mean, it is not a proper gauge fixing because it doesn't distinguish. You lose the distinction between two distinct gauge invariant states where you have defined gauge invariance in the loser sense. But when I say that there are different equivalence classes, well, what I said before with pi pn, I said it's a many-to-one relation. There's many kinematic states that map to the same physical state. You can make the same. Now, when I say in the same equivalence class, I mean with respect to the G-twirl, incoherent G-twirl. What I said before with pi pn is the coherent group average, and I define equivalence relations with respect to that. Here, I have to define the equivalence relation with respect to the incoherent G-twirl. It's a different one. So it leads to different equivalence classes. But that's the way you would define it if that's the route you want to go, because of the statement that the G-twirl in the case of G compact is an orthogonal projector onto the G invariant subalgebra. This means that any state that obeys this condition you get by projecting kinematical states with this G-twirl. You cover everything with that. And then, I will also have the case that there's several kinematical states that map to the same G-twirl state. So they are an equivalence class with respect to this G-twirl. And the statement is that these guys here, they lie in different equivalence classes with respect to the G-twirl. That's why I get two different answers. And then the gauge fixing, the point is that gauge fixing is not adapted to the incoherent G-twirl, to the equivalence classes of the incoherent G-twirl. It is adapted to the equivalence classes of the coherent G-twirl.
Any more questions? Okay, so if no, then let's thank Philipp.